Hi guys, welcome to Reason Realm. And in this video, we're going to be solving this question under the topic of stress and strain physics. So let's go straight into the question. The question says, a wire of length 1.7 meters hangs vertically from a fixed point as shown in the figure below. The wire has a cross-sectional area of 5.74 times 10 to the power 8 meters squared and is made of a material that has a Young modulus of 1.6 times 10 to the power 11 pascals. A load of 25 newtons is hung from the wire. And the first question says calculate the extension of the wire. So this first question is actually very easy. It's actually very easy. The first thing that you have to know is the equation that connects stress and strain, which is stress is just equal to the Young's modulus multiplied by strain. Okay, and you know that stress is the load or the force over the cross-sectional area of the wire. Then strain is just simply the extension divided by the initial length of the strain. So in this question, we've been asked to find the extension of the wire. So in short, we'll be finding this. And notice we already have the original length of the wire, which is 1.7 meters, the force 25 newtons, and the cross-sectional area was given there. So it's actually very easy from there. Let's make the extension the subject of the formula. If we do so, we will have the force multiplied by the initial length over the Young's modulus multiplied by the cross-sectional area. Okay, from here we can just replace the force is 25 newtons. The initial length is 1.7 meters. Okay, the Young's modulus is 1.6 times 10 to the power 11 pascals. And the cross-sectional area is 5.74 times 10 to the power negative 8 meters squared. So punching this into the calculator, we get we get that our extension will be equal to 4.63 times 10 to the power negative 3 meters. So that's our answer right there for question part 1. So let's go to part 2 now. What does part 2 say? Part 2 says the same load is hung from a second wire of the same material. So that means the Young's modulus is maintained. This wire is twice the length but the same volume as the first wire. State and explain how the extension of the second wire compares to that of the first. Okay, so they're saying the same wire, but it is twice the length. The second wire is twice the length of the first wire, but both wires have the same volume. Okay, all right. Now I want us to visualize this so that we understand better what is being said here. So we have the first wire. Let's say this is our first wire. Okay, yeah, that is our first wire. Then they're saying the second wire is twice. Is that twice? I highly doubt. Let me draw it properly for you guys. Okay, start from there. You can go up to somewhere there. Yeah, seems fair. Now, from your perception, do you think that the volume of the first wire, this is wire 1, is equal to the volume of wire 2? I highly doubt, because if the length was doubled, then the volume should automatically differ, as in the volume of the second wire should be greater than the volume of the first wire. Henceforth, if you think of it again, the volumes of the two wires will only be equal if the volume of the second wire, or I mean the cross-sectional area of the second wire, was reduced by half after its length was doubled. Then and only then will the two volumes be equal. Okay, let me show you what I mean again. Imagine it's right wire 1 there, and let's write wire 2 there. So wire 1 has a volume V, a length L, a cross-sectional area A. Wire 2 has a volume V, which is the same as wire 1, but it has twice the length. Now notice this, the volume of wire 1 will be equal to the cross-sectional area multiplied by the length of the wire. Think of it more of like the volume of a cylinder, which is the area of the base area there multiplied by the height, which is in short the length of the wire. Okay, now what will the volume of wire 2 be then? The volume of wire 2 will be the cross-sectional area A multiplied by the length of the wire 2L. Now notice that this term and that term over there are not the same. Remember, we said the volume of wire 1 is equal to the volume of wire 2, and from these expressions we're having here, they clearly are not equal. They would only be equal if we reduced the area by half, because once we do that, this 2 and that 2 can cancel, and then we'll have the volume will be equal to AL. Okay, then those two will be equal right there. I hope that makes sense. That is the reason why even here on this diagram here, I say they would only be equal if this was reduced by half, as in the cross-sectional area, that distance from there was reduced by half. Okay, therefore we know that the cross-sectional area for wire 2 is simply the cross-sectional area of the first wire divided by 2. Okay, so now we can use this relationship over here to help us determine the relationship between the extension of the second wire and that of the first wire. Okay, so we know the extension is equal to the force times the initial length divided by the Young's modulus multiplied by the cross-sectional area. Okay, so the extension of the second wire, let's name it delta L naught, will be equal to the force, since both wires had the same force, and the length, which was 2L, or which is 2L. The Young's modulus, which didn't change because the materials were the same, and the area, which is that. So simplifying this, we get 4 FL divided by A. Now, if you notice here, this is just the same as that, and this right here as well is the extension of the first wire. Okay, so in short, what we have here is the extension of the second wire will be equal to 4 times the extension of the first wire. The extension of the second wire will be equal to 4 times the extension of the first wire. That means the extension of the second wire is much greater than the extension of the first wire, which makes a lot of sense actually, because if you look at the structure of the first wire is just more like that. It's very thick and it's very short, but the second wire is very thin and very long. It makes sense. This wire would indeed have a longer extension, unlike this wire over there. Okay, so if you want to finish this with a statement, you can say the extension of the second wire would be, or let's say is, 4 times the extension of the first wire. Okay, so we're done. Alright guys, this is the end of this video. I hope you liked it. Please don't forget to like, subscribe, and also turn on the notification bell so that you would get alerts anytime I update the video. Once again, thank you guys for watching. Please subscribe. That would really help my channel a lot. Bye guys, see you in the next video.